Synthesizing pure primary amines can be challenging because standard alkylation often leads to a mixture of products. The Gabriel Phthalimide synthesis provides a sophisticated solution, allowing for the controlled production of primary amines with high purity and no secondary or tertiary bypass. In simple nucleophilic substitution, the resulting amine is more nucleophilic than the starting material, leading to unwanted multiple alkylations. To avoid this, we use a protected nitrogen source that can only react once. This is where phthalimide becomes essential. Phthalimide is the star of this process. Its nitrogen atom is flanked by two carbonyl groups, which stabilize a negative charge through resonance. This makes the NH bond relatively acidic and ready for deprotonation by a base like potassium hydroxide. The synthesis begins by reacting phthalimide with potassium hydroxide. This acid-base reaction removes the proton from the nitrogen, creating potassium phthalimide. This salt contains a powerful nucleophilic nitrogen atom, now primed to attack an alkyl halide in the next step. In the second step, the phthalimide anion performs an SN2 attack on a primary alkyl halide. The nitrogen displaces the halide leaving group, forming N-alkyl phthalimide. Because the nitrogen is now bonded to two carbonyls, it is no longer nucleophilic, preventing further alkylation. This is the secret sauce of the Gabriel synthesis. The lone pair on the nitrogen is delocalized into the two carbonyl groups via resonance. This significantly reduces its nucleophilicity, ensuring that only one alkyl group is ever attached to the nitrogen atom. To release the free primary amine, the N-alkyl phthalimide must be cleaved. This can be done through harsh acidic or basic hydrolysis, but a milder and more efficient method often involves using hydrazine in a process known as the Ingmansky procedure. Hydrazinolysis is preferred because it occurs under milder conditions. The hydrazine attacks the carbonyl carbons, breaking the CN bonds and releasing the primary amine. The byproduct, phthalhydrazide, precipitates out, making the purification of our desired amine very straightforward. Let's look at an example, synthesizing ethylamine. We start with potassium phthalimide and add ethyl bromide. The SN2 reaction creates N-ethyl phthalimide, which is then treated with hydrazine to yield pure ethylamine and the solid phthalhydrazide byproduct. Similarly, for benzylamine, we use benzyl chloride. The nucleophilic nitrogen attacks the benzylic carbon. Despite the large phenyl group, the primary carbon is accessible for the SN2 attack, leading successfully to the primary benzylic amine after hydrolysis. A major limitation is the alkyl halide structure. Since the mechanism relies on SN2, tertiary alkyl halides cannot be used. Instead of substitution, the strong basicity of the phthalimide salt causes an E2 elimination, resulting in an alkene instead of an amine. Aryl halides and vinyl halides are also incompatible. The SN2 mechanism requires a backside attack on an sp3 hybridized carbon. The electronic and steric environment of benzene rings or double bonds prevents this, making it impossible to synthesize aniline directly this way. Secondary alkyl halides are a gray area. While they can react, the reaction is significantly slower due to steric bulk, and there is often competing E2 elimination. This results in lower yields of the desired primary amine compared to primary alkyl halides. To summarize the mechanism, first, we deprotonate phthalimide to create a nucleophile. Second, we perform an SN2 alkylation on a primary halide. Finally, we use hydrazine to cleave the intermediate and release the pure primary amine. The Gabriel synthesis is a powerful tool for organic chemists. Its main advantage is the total avoidance of secondary and tertiary amine contamination, provided you respect the limitations of the SN2 pathway and use appropriate starting materials. Quick check, which can we make? Aniline is an arylamine, no, and tert-butylamine comes from a tertiary halide, no. Isopropylamine is possible, though yield may be lower, making B the only viable answer among these choices. Mastering the Gabriel Phthalimide synthesis allows for precise control in nitrogen chemistry. By understanding the SN2 requirements and the role of resonance stabilization, you can effectively plan the synthesis of complex primary amines. Generated by Vision Solve AI.